Hi, Stu Schwartz from MasterMathMentor.com. This is video AB19a. The topic is function analysis, and it covers the AB manual, pages 109 to 112.
Did you ever notice that in your pre-calculus class, most of the functions you dealt with were factorable? When they were factorable, there was a bunch of things that you could do. You could find the y-intercept, you can find roots, you could find intervals where the curve was relative to the x-axis, whether above or below. When it was unfactorable, unless it was in a special form, the only thing that you could really do was get the y-intercept and perhaps plug in some points to get a sense of what the curve was doing. In calculus, we will find that whether the function is in factored form or unfactored form, we can determine the actual shape of the curve and also its high and low points. This section is called function analysis, and you will be really amazed at what you can do to find all aspects of a function using calculus techniques. We will say that a function is increasing when the y value increases as the x value increases. So as we read the graph from left to right, the curve goes up. So on the graph below, we say that this function is increasing on the interval b to infinity. A function is decreasing when the y value decreases as the x value increases. So as we read the graph from left to right, the curve goes down. So the function below decreases on the interval negative infinity to a. A function is constant when the y values stay the same as the x values increases. As we read the graph from left to right, this curve stays flat and is constant. So we'll say that this curve is constant on the interval a to b. We go into a little bit more depth. Assuming that x2 is greater than x1, we define an increasing function if f of x2 is greater than or equal to f of x1, and a strictly increasing function if f of x2 is greater than f of x1. The same is true with decreasing functions. If f of x2 is less than or equal to f of x1, we will call it decreasing. But if f of x2 is less than f of x1, we call it strictly decreasing. We see the distinction in the graph. In an increasing function, it's possible for the graph to be flat in sections as long as the curve never decreases. But in a strictly increasing function, the graph is never flat. This curve is f of x equals x minus 1 quantity cubed. And if we choose two values, x2 and x1, such that x2 is greater than x1, then f of x2 will always be greater than f of x1. So this curve is strictly increasing. Strictly increasing curves come in three varieties, as shown. Stop the video and on each curve draw tangent lines at the given points. It should be obvious that no matter where we draw a tangent line on an increasing curve, the slope, which is the derivative, is positive. Decreasing curves come in three flavors as well. Stop the video and in each case, draw tangent lines at points on the curves. It should also be obvious that on decreasing curves, the slope of the tangent line, which is the derivative, is always negative. So the sign of the derivative is instrumental in telling us whether a function is increasing or decreasing. So assuming that the function f is continuous and differentiable on the interval AB, then this can be summarized by looking at the sign of f prime of x for all x in the interval AB. If f prime of x is positive, then f is increasing on the closed interval AB. If f prime of x equals 0, then f is constant on the closed interval AB. And if f prime of x is negative, then f is decreasing on the closed interval AB. This is important. It tells us that if we know the sign of the derivative in specific intervals, then we also have information about the behavior of the function itself in that interval. What makes this rule doubly important is that, as we saw, it works in reverse. So if f is increasing on the interval AB, that means that f prime of x is positive on that interval. If f is constant on the interval AB, that means that f prime of x equals 0 on that interval. And if f is decreasing on the interval AB, that means that f prime of x is negative on that interval. In trying to determine the behavior of functions, whether they're increasing, decreasing, have horizontal or vertical tangents, it is best to go through a procedure. We will outline that now. First, we need to define a term called critical values. Critical values are values of x where one of the following is true. F prime of x equals 0, meaning that there are horizontal tangents at x, or where f prime of x does not exist. At those places there could be vertical tangents, asymptotes, cusp points, or corners. Here's the procedure. We first find f prime of x using our derivative rules and express it as a fraction. It is best to have both numerator and denominator in factored form. We then find the critical values. We set the numerator and denominator of f prime of x equal to 0 and solve. We take all of our critical values and create a sign chart of f prime of x. We test numbers in each interval to determine the sign of f prime of x. And utilizing the rules that were just stated, we can determine whether the function is increasing, decreasing, the locations of horizontal tangents, or where dy dx does not exist. In problems 1 through 4, you are given functions and you're asked to find intervals where the functions increase and decrease, showing all work. We first take the derivative and get 12x minus 3x squared and set it equal to 0. We put it into factored form, 3x quantity 4 minus x equals 0, giving the critical values x is equal to 0 and x is equal to 4. We now make a sign chart with those two critical values listed, and we put little zeros above those values to indicate that the tangent line at those critical values are horizontal. We then have 3 intervals and we test numbers into the derivative within those intervals. For instance, if x is a number less than 0, like -3, the derivative will be negative times positive, which is a negative. If x is a number between 0 and 4, like 2, the first derivative is positive times positive, which is a positive. And if x is a number to the right of 4, like 6, the derivative is positive times negative, which is negative. Note we do not care about the numerical values, just the sign. Interpreting the sign chart, we conclude that f is increasing on the interval 0 to 4 and decreasing on the interval -infinity to 0 and 4 to infinity. We use a union sign to show that it is both intervals. We do not make a distinction whether we use open intervals or closed intervals. I said that f is increasing on the open interval 0 to 4. The closed interval would be just as correct. We then show the problem graphically and confirm that the graph is increasing on 0 to 4 and decreasing everywhere else. Number 2 reads f of x equals x minus 2 quantity squared times quantity x plus 1. We could multiply that out, but it is easier to use the product rule. We get the derivative is x minus 2 quantity squared times 1 plus x plus 1 times 2 times x minus 2 times 1. Expanding all that, we get 3x quantity x minus 2 is equal to 0, leaving our critical values at 0 and 2. Our sign chart is shown with 3 intervals that alternate positive, negative, positive. So we conclude that f is increasing from -infinity to 0, union 2 to infinity, and decreasing on the interval 0 to 2. Again, the graph is a good confirmation of our answer, and we see that we have 2 horizontal tangents, x is equal to 0 and x is equal to 2 are the locations. It should be pointed out that on both curves, we have a sense of the shape of the curve, but not how low it gets and how high it gets. In number 1, we know that the curve decreases, then increases, then decreases, but we do not know how low it gets and how high it gets. The same is true on number 2. That is coming up in the next section. Problems 3 and 4 are 2 functions that are in the form of quotients. When we have those forms, we should always think about the domain of the function. Problem 3 reads f of x equals x minus 2 over x plus 6. In our pre-calc days, we would realize that there is a vertical asymptote at x is equal to -6. We start by taking the derivative, and we get, by the quotient rule, we square the bottom, and upstairs we get x plus 6 minus quantity x minus 2, giving 8 over x plus 6 quantity squared, and we set that equal to 0. There are no values that make that equal to 0, as the numerator is never equal to 0. However, we are also concerned for our critical values where the denominator equals 0 and x equals -6 is a critical value. In our sign chart, our only critical value is x equals -6, and above it we write an infinity sign to indicate that the derivative does not exist there. However, on intervals to the left of -6 and to the right of -6, the first derivative is positive. So we conclude that the function is increasing from -infinity to -6, union -6 to infinity. Note that it would be wrong to say -infinity to infinity because at x is equal to -6, the function does not exist. Our graph confirms our answer. We have a vertical asymptote at x is equal to -6, and the curve is increasing to the left of it and increasing to the right of it. Notice that we are just getting the curve's shape. We could get other information from our pre-calculus, knowing that this has a 0 at x is equal to 2. We could also use limits to find that the limit of f of x as x approaches infinity or -infinity is 1, giving the curve a horizontal asymptote at x is equal to 1. But right now we're just interested in intervals of increasing and decreasing. Number 4 reads f of x equals x squared over x squared minus 4. And again, from our pre-calculus knowledge, we know that this has vertical asymptotes as x is equal to plus or minus 2. We take the derivative, squaring the bottom, and upstairs we get x squared minus 4 times 2x minus x squared times 2x. And that leaves us with negative 8x over x squared minus 4 quantity squared equals 0. Our critical values are where the numerator equals 0, x is equal to 0, and where the denominator is equal to 0, x equals negative 2 and 2. In our sign chart, we put our 3 critical values, and above the negative 2 and 2, we put infinities, while above the 0, we put a 0. This creates 4 intervals, and they are plus, then negative, then negative. So we conclude that the function is increasing from negative infinity to negative 2, union negative 2 to 0, and decreasing on the interval 0 to 2, union 2 to infinity. Our graph confirms our answer. Note that we have vertical asymptotes at x equals negative 2 and x is equal to 2. Our graph increases to the left of negative 2 and then increases again up to 0. It then decreases from 0 to 2 and also from 2 to infinity. We could have also asked whether there are horizontal asymptotes, and there are, which is the limit of f of x as x approaches plus or minus infinity, which would be 1. Let's look back at number 4 for a second. We were told that f of x equals x squared over x squared minus 4. On the AP exam, you may be asked this question. In what intervals is f increasing? Justify your answer. Many times the AP exam asks students to justify an answer. We will see what that means. So you go through the process we just did, taking the derivative, setting it equal to 0, finding the critical values, making a sign chart, and then coming up with your answer. The AP graders have allocated 3 points for this problem. 1 point for taking the derivative and setting it equal to 0, 1 point for the answer, and 1 point for the justification. You may be surprised to find out that you would only receive 2 of the 3 points. Why? In the AP exam, a sign chart is never a justification. Now, you may still make a sign chart. In fact, I recommend doing it. It gives you a lot of information. However, the sign chart alone will never justify the answer to a question. So to receive full credit, this is what you must write. F is increasing on the intervals negative infinity to negative 2 and negative 2 to 0 because f prime of x is greater than 0 on those intervals. You are simply stating exactly what the sign chart states. However, you are doing it in sentence form. That is a justification. So do not just leave a sign chart. Do not make the readers interpret what you are trying to say. State it. We will now define 2 new terms with which you will become very familiar in this course, relative minimum and relative maximum. We have a test to determine whether a curve contains a relative minimum or relative maximum. It is called the first derivative test. It says that we have a function f be differentiable on some interval ab containing c. Then we can classify f of c in one of several ways. First, If f prime of x changes from negative to positive at c, then we say that f has a relative minimum at the point c, f of c. Think of a relative minimum as the bottom of the hill, as shown in the left figure below. Second, if f prime of x changes from positive to negative at c, then f has a relative maximum at the point c, f of c. Think of a relative maximum as the top of a hill, as shown in the middle figure below. Third, if f prime of x is both positive on both sides of c, or both negative on both sides of c, then the point c, f of c is neither a relative minimum or a relative maximum, as shown in the right figure below. Fourth, be sure that for x equals c, found in 1 and 2, that f of c does exist. If not, then there is no relative extrema at x is equal to c. Relative extrema is a term for either a relative maximum or a relative minimum. A curve can have more than one relative minimum and relative maximum. The terms we use for this are relative extrema or sometimes local extrema. A relative minimum or maximum is not to be confused with an absolute minimum or absolute maximum, which represents the highest and lowest point on the curve within the given interval. We will spend more time with this in a later chapter. The curve you see on the screen has two relative minima and one relative maximum, a total of 3 relative extrema on the interval AB. Problems 5 and 6 ask you to find relative extrema of the given functions. When we say to find a relative extrema, we're interested in the x value where these occur. 5 reads f of x equals 5x to the fourth minus 20x squared. Our first job is to find the first derivative, which is 20x to the third minus 40x. We factor that into 20x, quantity x squared minus 2, and set it equal to 0, getting x is equal to 0 and plus or minus square root of 2. We then make a sign chart with negative square root of 2, 0, and square root of 2, where the tangent lines are horizontal. That gives 4 different intervals, and our sign chart alternates negative, positive, negative, positive. So we find that there is a relative maximum at x is equal to 0 because f prime of x switches from positive to negative. There is a relative minimum at x is equal to negative square root of 2 and also square root of 2 because f prime of x switches from negative to positive in both cases. We weren't asked to confirm graphically, but we will do so. It's clear that the curve has a relative maximum at x is equal to 0. And the relative minimum are at both x is equal to negative square root of 2 and positive square root of 2. Note that we do not know how low this curve gets at these relative minimum. What we would have to do is plug square root of 2 into the original expression to find f of plus or minus the square root of 2. In 6, the equation is very similar, but we get a very different result. F of x equals 5x to the fourth minus 20x to the third. We take the derivative and we get 20x to the third minus 60x squared. We factor and get 20x squared times the quantity x minus 3 equals 0, giving 2 critical points, x is equal to 0 and x is equal to 3. Our sign chart shows that f prime of x will be negative to the left of 0, negative between 0 and 3, and positive to the right of 3. So we find that the f has a relative minimum at x is equal to 3 because f prime of x switches from negative to positive. This curve has no relative maximum. Our graph confirms this. We see that there is a relative minimum at x is equal to 3, and the y value is well below negative 100. Notice that at x is equal to 0, the curve levels off. There is no relative minimum, there is no relative maximum.
7 and 8 prove a little bit more difficult in finding relative extrema because of using trig and the possibility of vertical tangents. In number 7, we have f of x equals cosine of x plus 1/2 x on the interval 0 to 2 pi. We take the derivative and get negative sine of x plus 1/2, set that equal to 0, and sine of x equals 1/2, and x equals pi over 6 and 5 pi over 6. Note we are working in radians. Making the sine chart, we use the endpoints of 0 and 2 pi and put our critical points where the derivative is equal to 0 at pi over 6 and 5 pi over 6. And we find that our sine chart alternates going from positive to positive, leaving us with a relative maximum at x is equal to pi over 6 and a relative minimum at x is equal to 5 pi over 6. This is confirmed in the actual graph of the function. Notice that you would not have the heights of the curve, just the general shape from the first derivative work. You would have to plug in x is equal to 0, 2 pi, pi over 6, and 5 pi over 6 into the original function to get a sense of the height. In number 8, we have f of x equals negative quantity 36 minus x squared to the 2/3 power. We will treat this as a power rule and bring the negative 2/3 in front, having 36 minus x squared to the negative 1/3 times the derivative of 36 minus x squared, which is negative 2x. And that leaves us with 4x over 3 quantity 36 minus x squared to the 1/3 power. We set both numerator and denominator equal to 0, and we get x is equal to 0 and x is equal to plus or minus 6. In our sine charts, at x is equal to plus or minus 6, we get the derivative is infinite, and at x is equal to 0, the derivative is 0. Testing numbers, we find that our sine chart alternates plus, minus, leaving us with a relative minimum at x is equal to 0 and relative maximum at x is equal to plus or minus 6. The graph shows one important aspect of the process. Notice that the derivative is undefined at x is equal to plus or minus 6, but the function is defined at x is equal to plus or minus 6. Its value is 0. So we have vertical tangents there, and we do have a relative maximum at those points, even though they are cusp points. You can still think of them as the top of a hill. We are not through with function analysis. We may know that the derivative of a function is positive in some interval, and thus the function is increasing in that interval. But how do we determine which of the 3 increasing curves the shape of our curve resembles in that interval? Stay tuned to video 19b to get the last piece of this puzzle.